Pluto, once categorized as a distinct and legitimate planet in our solar system, was considered a special object for many years. However, recent discussions led by famous astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited debate about Pluto's status, prompting further analysis of its role in the cosmos. These scientists have suggested that Pluto could potentially be on a collision course with Neptune, sparking a wave of questions. How could such a massive event unfold? What would the impact mean for both planets and the 34-second solar system at large? Are we witnessing a rare and unique cosmic occurrence, or is there a more intricate and profound explanation behind this theory? Let's delve into what a possible Pluto-Neptune collision might imply. Once considered a smaller, more distant object in the solar system, Pluto still generates substantial interest among scientists. According to key studies from leading experts, Pluto's orbit is dangerously close to Neptune's, causing some astrophysicists, including Tyson and Kaku, to express concern about the 1 minute and 7 seconds possibility of a catastrophic impact between the two. The central question now is whether such an event poses a real threat to Earth. How could this happen in the first place? Pluto's orbit is one of the most unusual in our solar system. It takes an extraordinary 248 years to complete one full orbit around the Sun, meaning that since its discovery in 1930, Pluto has not yet completed a single orbit. However, its orbit isn't the only distinctive feature. It is also highly elongated compared to the more 1 minute and 39 seconds circular orbits of the larger planets. Additionally, Pluto's orbit is tilted by 17 degrees relative to the plane of the solar system, making it one of the most tilted orbits observed. This extreme tilt, combined with its elongated shape, adds complexity to Pluto's journey through space. A particularly fascinating aspect of Pluto's orbit is its interaction with Neptune's orbit. For around 2 decades during each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect in terms of planetary positioning. This raises an 2 minutes and 13 seconds important question. Why haven't Pluto and Neptune collided yet? The answer lies in the gravitational forces at play within the solar system. Immediately after Pluto's discovery, astronomers were puzzled by its orbit. Unlike the other planets, which follow relatively flat, aligned paths within the solar system, Pluto's orbit is tilted and elliptical, making it a subject of intense study. The fact that Pluto's orbit crosses Neptune's doesn't automatically result in a collision due to a gravitational interplay that stabilizes the two orbits. 2 minutes and 48 seconds. This balance, referred to as the three-body problem, illustrates how Pluto, Neptune, and the Sun interact through their gravitational forces. Predicting future positions based on their current motions and forces exerted upon each other highlights how the gravitational pull between Pluto, Neptune, and the Sun ensures the two objects never collide. Astrophysicists note that this stable interaction is maintained by a mechanism called libration, which ensures that when Pluto crosses Neptune's orbit, it does so at 3 minutes and 19 seconds, least 90 degrees away from Neptune. This ensures that the two bodies are never at the same point in their orbits at the same time. Additionally, Pluto's orbit exhibits degree libration, meaning it oscillates or shifts around its path. This mechanism further reduces the risk of collision. Another important factor in Pluto's orbital stability is the gravitational wobble effect, known as VZK wobbling, which explains how the gravitational pull from Pluto, Neptune, and the Sun influences each other, helping to maintain Pluto's orbit. 3 minutes and 51 seconds. Despite its seemingly erratic path, the three-body problem and these forces that govern celestial motions are critical to understanding how planetary orbits evolve. These interactions not only shed light on Pluto but also enhance our knowledge of the broader workings of the solar system. Numerical simulations conducted in the 1980s revealed that while stabilizing forces helped keep Pluto's orbit stable, slight changes in its initial conditions could cause its orbit to become more erratic over long periods. Despite such 4 minutes and 22 seconds potential irregularities, Pluto's orbit has remained relatively consistent over millennia. Recent models have further highlighted how planets like Jupiter, Saturn, and Neptune help stabilize Pluto's path. For example, Neptune and Pluto follow a resonant orbit, meaning that for every 2 orbits Pluto completes, Neptune completes 3. This resonance is crucial to maintaining Pluto's orbital stability. However, Neptune is not the only planet influencing Pluto's orbit. Jupiter's gravitational influence also plays a significant role. Even 4 minutes and 58 seconds. Saturn has been shown to help stabilize Pluto's orbit. These simulations suggest that Jupiter's gravity alone could maintain Pluto's orbit for billions of years, if not indefinitely. The cooperation of Neptune, Jupiter, and Saturn is thus essential for ensuring Pluto stays on its current course. Without these stabilizing forces, our solar system would be more chaotic, with bodies like Pluto potentially colliding with others or being ejected from their orbits entirely. Studying such interactions not only helps us 5 minutes and 29 seconds understand Pluto's orbit, but also gives us valuable insights into the larger workings of the universe. And so on, this pattern of punctuation and formatting would be applied throughout the text. While current models suggest that Pluto and Neptune's orbital resonance prevents a collision, the long-term evolution of their paths remains uncertain. Small gravitational perturbations from other planets, passing asteroids, or even the hypothetical Planet 9 could introduce unpredictable shifts in their trajectories over millions or billions of years. If a disruption were to occur, sending Pluto on a direct collision course with Neptune, the consequences would be staggering. A high-speed impact between the two would likely shatter Pluto into countless fragments, forming a new debris field within the outer solar system. Some of this debris could be captured by Neptune's gravity, potentially creating new moons or rings around the gas giant. Other fragments might be ejected into the Kuiper belt, or even further into interstellar space. 17 minutes and 45 seconds. More alarmingly, certain ejected pieces could eventually drift inward toward the inner solar system. If any of these remnants were large enough and their paths aligned with Earth's orbit, they could pose a significant impact threat. While Earth is protected by Jupiter's massive gravitational field, which often deflects or absorbs incoming objects, the possibility of Pluto's remnants entering the asteroid belt and disrupting its structure could not be ignored. Beyond immediate physical consequences, the loss of Pluto as a celestial body would mark a significant shift in our understanding of planetary dynamics. Scientists have long studied Pluto as a key example of a trans-Neptunian object, and its destruction would deprive astronomers of valuable insights into the early solar system. 18 minutes and 30 seconds. In response to these potential threats, space agencies worldwide have begun investing in more advanced planetary defense initiatives. NASA and ESA have proposed expanding their asteroid tracking systems to include Kuiper belt objects, while private space companies are exploring deflection technologies that could, in theory, alter the orbits of dangerous celestial bodies before they reach Earth. Meanwhile, debate rages on in the scientific community. While many experts argue that Pluto and Neptune's resonance will continue protecting them for eons, others caution that celestial mechanics are far from absolute. The gravitational influences of unknown objects, passing rogue planets, or even the hypothetical existence of dark matter interactions could introduce variables that current models fail to predict. 19 minutes and 12 seconds. As humanity watches and waits, Pluto continues its slow, solitary voyage through the frozen depths of the solar system. For now, its fate remains written in the intricate gravitational ballet of the cosmos, a delicate balance that could, one day, tip unexpectedly, reshaping our understanding of planetary motion forever. Despite the prevailing consensus that Pluto and Neptune's orbits are stable, an increasing number of astrophysicists are beginning to question whether previously overlooked factors could alter this delicate balance. Recent advancements in observational technology, such as next-generation space telescopes and AI-driven orbital simulations, have allowed scientists to examine Pluto's trajectory with unprecedented precision. To their astonishment, some simulations suggest that over the course of several million years, minor gravitational nudges from passing objects, such as undiscovered Kuiper belt bodies, rogue planets, or even shifting mass distributions within Neptune itself, could accumulate, gradually pulling Pluto's orbit into a more chaotic state. Would this be enough to disrupt Pluto's resonance with Neptune? Could an impact, once considered impossible, become a reality in the distant future? 20 minutes and 15 seconds. Meanwhile, deep in a research facility on Earth, a team of planetary scientists led by Dr. Ilara Voss is running high-fidelity gravitational models in real time. Their goal: to determine the exact conditions under which Pluto's orbital stability could break down. According to these results, Dr. Voss says, staring at the projections on her screen, if even a minor Kuiper belt object were to shift Pluto's velocity by just a fraction of a meter per second, its orbit could deviate significantly over the next billion years. If the right conditions align, a collision could be inevitable. The room falls silent. The implications of this discovery are profound. A cosmic event of this magnitude, one that could reshape the outer solar system, might already be in motion, its seeds sown millions of years ago by forces beyond human control. 21 minutes. Elsewhere, at a deep space observatory orbiting beyond the Moon, an automated telescope detects an unusual mass in the outer solar system. It's moving faster than expected, too fast for an ordinary Kuiper belt object. Data is transmitted back to Earth, where AI algorithms analyze the findings. What they discover is both thrilling and terrifying. This object isn't just any asteroid. It appears to be an interstellar visitor, much like Oumuamua or Borisov, but with one crucial difference. Its trajectory suggests it has already interacted with the solar system's outer planets, subtly influencing their orbits in ways that had previously gone unnoticed. If it had passed close enough to Neptune in the past, could it have already initiated the first steps toward disrupting Pluto's stable resonance? 21 minutes and 45 seconds. Back at the research facility, the team works tirelessly to refine their models. As they run new simulations incorporating this unknown object's gravitational influence, the results send a chill down their spines.